Okay, this is the review for gas laws. Okay, so as far as relationships are concerned, we're talking pressure, volume, and temperature. Okay, most of the stuff we have is a closed system. That means that the number of particles stays the same. We're not worried about how the number of particles changes. But um, you need to know how pressure and volume and temperature interact. Okay, remember that pressure, the key about pressure, it's collisions. So we assume that pressure comes from the collisions of the particles with the walls of the container. Okay, so anything that increases those collisions increases pressure. Anything that decreases the collisions decreases pressure. So if we're looking at volume, volume is the space. As volume goes up, more space is going to give the particles less collisions. So your pressure is going to go down. This is Boyle's law. Okay, Boyle's law also says that pressure times volume, the quantity of pressure times volume at a constant temperature and fixed amount of particles is a constant. That's a hyperbola. So what that looks like is this. Pressure, volume, this is like our Boyle's Law lab. It's a nice curve that shows the indirect relationship. So this is an indirect relationship. As one goes up, the other goes down. Okay, now we've got temperature. As temperature increases, the particles are moving faster. If they are moving faster, temperature is the same thing as average kinetic energy, by the way. As the particles move faster, they are going to collide with the walls more and more. So your pressure is also going to increase. This is a direct relationship. As the particles move faster, there are more collisions. Okay, and we have a pressure and temperature relationship that looks like that. Okay, pressure increases, temperature increases. The last relationship we need to look at is volume and temperature. All right, as the particles move faster, so as your temperature goes up, they need more space, or they take up more space. So our volume is going to go up too. This is Charles's law. So as temperature goes up, volume goes up. Our graph for that, we've got a V and a T. It's going to look the same as the pressure and temperature. So be ready to predict that. What are these graphs going to look like? Recognize the graphs for them, and be aware of recognize the graphs for them, and just be aware of these relationships. Remember that pressure and collisions are going to help you predict what is going to happen. Okay. Additionally, we talk ideal gases. Okay, that's the kinetic molecular theory. There are a whole bunch of ideas with the kinetic molecular theory. One of them is, let me erase this and we'll start there. Kinetic molecular theory says there are no intermolecular forces in a gas. Okay, no intermolecular forces in a gas. That means it can't be solidified and can't be liquefied, cannot change phase. Okay, it also said that speed equals average kinetic energy. The speed of the particles is directly related to the temperature of the particles. The volume of the particles is negligible. That means you can ignore it because they're so far apart. It says the particles are moving in random, constant, linear, that means straight lines, motion. And it says they do transfer energy, but don't lose any energy. Like no net loss of energy. Okay? Those are the postulates of the kinetic molecular theory. Ideal gases obey all of these. There's no such thing as a truly ideal gas. Hydrogen and helium are your most ideal gases because they're tiny and they move really fast. Okay? Additionally, the best conditions for an ideal gas are hot with no pressure, just like an ideal relationship. High temperature, low pressure. These are the best conditions for an ideal gas. Ideal conditions for an ideal gas. Okay? All right. Using the ideal gas law. Okay, you can also get some stuff from your relationships right in this law. If you divide by them, okay, so if you're dividing like pressure and temperature and pressure and volume, Those are direct relationships. Okay, so divide means direct. DD. Okay, if you multiply, it's indirect. Okay, using this formula. If they tell you STP, you're going to look at table A. Must use table A for STP. You should have, there's 2 temperatures and 2 pressures. Temperature, always use Kelvin. Kelvin. Not Calvin, but Kelvin. And pressure, match the units. Okay, so make sure when you choose your standard pressure, you match the units. Match of the problem. That's how you know whether to pick atmospheres or kilopascals. Okay? When you're using this formula, PV over T equals PV over T, if something is constant, it cancels out. Okay? So if it's at constant temperature, your temperature would essentially go away, and you're left with Boyle's law. Okay? If it was constant volume, your volume goes away, and you're left with a different law. Okay? Last thing you need to know is when you're solving for this, I would suggest you do a knowns unknowns equations. Plug in what you know. You should only have one thing that you don't know. And then I will tell you to cross multiply, okay? Cross multiply to solve, because sometimes the math gets a little bit tricky and you guys love to break math, okay? Make sure your temperature is always in Kelvin. Kelvin. That means you add 273 if you have your Celsius temperature. Okay, so you always add 273 to get from Celsius to Kelvin. All right, Dalton's law and density. First and foremost, what you need to know about density. The density of a gas is the mass over the volume, like anything else, but we can just assume that we have a mole because it makes our lives easier. So it's the mass, this is going to be your molar mass from your periodic table, divided by 22.4. So if I ask you for the density of a gas, you just find the molar mass of it. For example, if I ask you for the density of CO2, that's all I have to give you. Any other information is extraneous. I'm going to take the molar mass of CO2. Carbon weighs 12 from your periodic table. Oxygen weighs 16. I have 2 of them. The total is 44. Okay? So if I want the density of CO2, I'm going to take 44 and divide it by 22.4, and I should get something a little bit less than 2. Okay? So I'm going to say about 2 grams per liter. This is grams, and this is liters. Okay? That's how you figure out density. Super easy. That formula is not on your reference table, the molar mass over 22.4, so make sure you memorize it. Dalton's law is partial pressures, okay? Dalton says that the total pressure of a mixture of gases is equal to the sum of the partial pressures of all the gases. So if I have hydrogen and helium in a mixture, the pressure of hydrogen is 30 kilopascals, the pressure of helium is 70 kilopascals. My total pressure is 100, okay? If I knew that my total pressure was 100 and I wanted to know the pressure of hydrogen, I would solve for X. Make sure you subtract 70 on both sides and don't divide. Again, make sure you do math. And you would get that X equals 30 kilopascals. The last way to do Dalton's law, the other way is with a mole fraction. And don't let the fact that it's mole fraction scare you, okay? It is just the percentage. How many of the particles are hydrogen? How many of the particles are helium? So if I have 2 moles of hydrogen and 1 mole of helium, I have 3 moles of gas total. So my whole sample is 3 moles of gas, okay? That's the whole. The part is the number of moles of each thing. So if I care about the number of moles of hydrogen, I'm going to say it would be 2 out of 3. So it's 2/3 hydrogen and 1/3 helium. Okay? So 2/3 of the total pressure is hydrogen, and 1/3 of the total pressure is helium. If my total pressure is 3 atmospheres, and my partial pressure of hydrogen is 2 out of 3, because 2 of the 3 moles are hydrogen, times the total pressure. And I would get 2. 2 atmospheres are due to hydrogen. I want to know the the partial pressure due to just helium. Take the mole fraction of helium, 1 mole of helium over 3 moles total, times the total pressure, which is 3, and I would get 1 atmosphere is due to helium. Okay? You can check your answers. 2 over here plus 1 over here should equal your total pressure, which is 3, which it does. Okay? Those are the 2 ways to do Dalton's law. Okay, last thing, vapor pressure. Vapor pressure is all on table H. If you get a weird question about 4 substances that you've never heard of, it's probably table H. Okay, propanone, ethanol, water, and ethanoic acid. What you need to know about this, any vapor pressure question with numbers involves you just reading from this graph, okay? Do not let it scare you. Just read it from this graph. What you do need to memorize, you need to know about this, is that ethanoic acid has high intermolecular forces, IFAs, and propanone has weak IFAs. Why? Because propanone evaporates easier. Okay, we say it's more volatile. So propanone evaporates easier. So it has weaker intermolecular forces. It's not held as tightly in the liquid. Okay? Ethanoic acid has very little vapor pressure. That means it has very little vapor, which means that it's not held as tightly it's held tighter in the liquid. Okay? And therefore it will not evaporate as easily. Okay? Normal boiling points are where they cross this dotted line. Okay? 101.3. So the normal boiling point of propanone would be the temperature associated here. Ethanol would be the temperature associated here. Water would be the temperature associated here. And ethanoic acid. Those are your normal boiling points. So normal boiling point is at standard pressure. Okay? Additionally, you need to know that a liquid boils when the pressure on the surface of it equals its vapor pressure. Okay? So, water boils at 100 if the pressure on the surface of it is 101.3. If you lower the pressure to 50, okay, I'm going to follow that over to water and go down, and it's 75, 80, let's say 83. So I can get water to boil at 83 degrees C if I lower the pressure on the surface of it to 50 kilopascals. Okay, that's what this says. But again, it's just reading the graph. Where does it cross that graph? Okay. Last thing to note, make sure you notice that the scales of these are different. Okay, the temperature goes up by 5s. Okay, the temperature goes up by 5s. Each grid line is 5 degrees. The vapor pressure goes up by 10s. Okay, each grid line is 10 kilopascals. When you are reading this, if you're reading off a graph, the Regents gives you a little bit of leeway, but it's usually plus or minus 1 or plus or minus 2. So make sure you read them very carefully, okay? If the answer is supposed to be 79, so if I asked you the normal boiling point of ethanol, and the answer is supposed to be 79 down here, and you tell me that it's 77 or 76, and you're not within the Regents, what the Regents or the answer key gives me, you may know what you're doing, but because you read it carelessly, I can't give you credit. Okay, so make sure when you're reading this graph, you read it very carefully. Temperature's got to be in Kelvin for pretty much anything except for this vapor pressure chart. You can see that it's Celsius. So make sure you're just reading off the graph. Otherwise, that should be everything that you need to know. Good luck.